Hello and welcome back. This is video number 7 of my Ultimate Ladybug course. In this video we will dive into indoor thermal comfort. It's a huge topic, loads to learn. We will look at the basics first. These are the most crucial to master and to understand, and we will see on how we can use Ladybug tools in order to revolutionize the way we analyze and design indoor environments. So grab a coffee and we will jump right in. Hold on, before we start, very important, member shoutouts. Get this, I got 5 new members, 2 rejoiners. I don't know what to say really. It's absolutely amazing for me, it really helps me. Honestly, it really helps me to continue this channel. Thanks for the support. So, first up we have Alex Lee, already joined 18 days ago. Sorry, I haven't made the shoutout because last video I was just cutting the one before you joined, but this time you're definitely in. Thanks a lot. Let's check out your channel. You have 1 subscriber, you have 7 videos. Good luck. I see you are into CFD analysis. The Jewel, part of the airport in Singapore, Terminal 4 I think. No, Terminal 3. I have seen it myself. Really interesting project. I hope I can actually learn some stuff from you as well and what you're doing. It seems like you have some Energy Plus playlists. That's interesting, really useful. Guys, check out his channel. I think it's quite interesting here, and his videos, of course. Then next up we have Edwin Gonzalez Meza, and I hope I pronounce it correctly, of course. No subscribers, no videos, but this doesn't really matter. Thanks for the support. I see you are long-time YouTube member. This is more than 10 years. Amazing. 11 years of YouTube, can you imagine? That says something. Thanks a lot, and let me know if you have any suggestions, questions. I'm always interested what people who watch my videos, what they do and why they're watching it and what they want to learn. Then we have Jana Tip Wee. I assume this is Thai, our Thai friend. Thanks for joining our channel. You have some playlists here I can see. I don't know what this is all about. Doesn't matter. Thanks for joining and thanks for the support. Then we have, this is a hard one. Let's see. Jalisa Sujivorakul. I don't even know what nationality, which culture that is. It doesn't matter. Everybody's welcome, and thanks a lot for the support. Thanks a lot for joining the team. Please, if you have any questions, suggestions, let me know. Then we have Arch Nazar. I hope. Or again, if I'm pronounced it correctly, I guess it's Architect Nazar. You have 14 subscribers, 3 videos. Good luck with your channel. Just let it grow. Staying in one topic is a good idea. Guys, check it out. Check out his channel. It's a flying drone module, basically. Interesting. Alright, good luck with your channel. If you have any questions, suggestions, video recommendations, I'm always up for it. Alright, then we have my 2 rejoiners. Combo45, I think you have been the longest to join my channel. Absolutely amazing. Thanks for the support. You rejoined 4 days ago. Is it already 1 year? Oh my god, it's already 1 year. Hey, I might need to start a new membership level, I guess, just for you. And Minimalev also rejoined 3 days ago. Again, this just reassures me that it seems like I'm doing something correct here in the channel. Great that you rejoined, and I can't wait to hear your thoughts, what you want me to cover maybe next. All right, now grab your coffee and we jump into indoor thermal comfort. Have you ever wondered why some buildings feel more cold or hot? Although the thermostat says it's 22 degrees, which is normally super comfortable. Well, that's the indoor thermal comfort, because there could be certain humidity or a draft, wind, and that's what we are trying to start to look at in this video. It will cover only the basics. We will only see how indoor thermal could look like in a certain environment, in a certain climate, in a certain environment, with our weather data. We will not look at the specific building. That will come later. This is the smaller brother, let's say, of Honeybee. Honeybee, which I made a series of already. You can dive into that if you want. but we will look at the basics in this video. We will also not solve the problem. We will try to understand the problem first. We're gonna try to understand with the weather data we created in the last videos. We look at the generic building and what could be the possible indoor comfort. And from there, we move to the next step. So it's really about understanding the tool first. What can we actually measure in Ladybug? And then from there, we go further. I also see this step as the beginning to formulate the goals for a project. It's always good to have a goal or a problem before you start designing. If you don't have a problem, then there's a problem. If you try to fix a problem, you automatically have a goal. If you can find the problem, then you automatically have a goal, and that's important to any design you do. If there's no problem, then you haven't done your analysis well, I think. If you don't know anything about what we did in the previous videos, please go back in the videos. It's kind of crucial to understand where we are. But I'm working on a real project. It's on a slow pace, but I try to really get my head around what's going on inside and what I could contribute in order to work it out. So go back and see what I discussed before, so you understand what it's all about. In this video, we will have a weather data. Maybe I go here into Grasshopper for you to better understand. All right, in Grasshopper, we imported weather data from an online source. Unfortunately, that weather data is not directly at the site where we have our project, so we had to modify the weather data so it fits our project better. It's not ideal, but the purpose to show you how you could modify your weather data. So even if you don't want to watch the previous videos on how to modify weather data, you can still use just a generic E+ weather data in order to follow along with this next steps. We just, in the previous also, we looked into how to import. So if you don't know about that, if you don't know these first portions, import and analyze data, then I highly recommend you go back in the playlist and watch these videos. Again, so this first portion is just us basically trying to manipulate the weather data which came from the airport, which came from Kigali. The output is just another weather data. Again, so you can use a generic weather data in order to understand the tool. You don't need to follow this whole step. You can plug in everything into the import weather E+ weather data. So this tool here is exactly the same as here. This is just our modified version of the weather data. And in the last videos, we looked into all kinds of things like how to construct data, how to deconstruct data, how analyze period works, wind speed, degree days, and so on. And then in the last two videos, we looked into the UTCI outdoor comfort and the PET comfort, which is both outdoor-based comfort studies. And it turned out that PET is much more accurate or takes other things into account. So that was very interesting. It also differentiates between male and female. That was very interesting, especially for this project. It will run by women, and that's why this really is very important to get that right, to understand what's going on. So this was outdoor comfort, and now today we look into these both tools, the adaptive comfort and the PMV comfort. They're a bit tricky to apply because it's going to be a mix of general analyzing the weather data. At the same time, it could be extended to quite a lot where it actually involves the model, but we will not working with a model yet because we don't have a model. So we will just use whatever we can use, however we can use the data we have at the moment. Again, so this was just us playing with data. This was the transformation of the weather data. This is our weather data now. This is the transformed weather data. This was the indoor and outdoor comfort. And we plotted these charts showing the different outdoor comfort models. The physiological equivalent temperature, which got us a very, very detailed idea on the weather, on the temperature, on the perceived temperature. And then we had the Universal Thermal Climate Index, which gave us quite a different look, strangely, really. So it's something I will explore more in future because I got very curious about the physiological equivalent temperature. seems like it's more refined, it's more accurate. Okay, nevertheless, indoor comfort. Okay, let's see what we can do. Ladybug tools, we are here. We will look into these two. Let's see if we can look at both, or if we need to split up the whole thing again. Ladybug adaptive comfort. This is actually supposed to be the first in the comfort series, but it's when I tried it the first time, I ran into some problems. All right, just to very quickly summarize, we have two models here. We have the adaptive comfort, we have the PMV comfort. Let's open both so we see what the difference are. Maybe we do it just together at the same time because it might help. We have similar inputs, different outputs, different calculation. The adaptive comfort is, as it's defined here, the adaptive thermal comfort model is for use on the interior of buildings where a heating or cooling system is not operational and occupants have the option to open windows for natural ventilation. Note that for fully conditioned buildings, the PMV thermal comfort model should be used. So this is for buildings which have no heating, no cooling. This is the PMV model is for buildings which are fully conditioned. As per definition, the PMV is thermal comfort model for use on the interior of buildings where a heating or cooling system is operational. For natural ventilated buildings, the adaptive thermal comfort model is recommended, and for outdoor conditions models such as the Universal Thermal Climate Index UTCI or physiological equivalent temperature are recommended for outdoor. So that's what we looked at last time. This is for conditioned buildings. This is for buildings without heating or cooling. We will try both. We will look at both. All right. So we have the outdoor temperature. The outdoor temperature we know. We have the dry pulp temperature. And well, it's because it's indoor. It's all about the air temperature around the occupant. Now, because we don't know anything about the space yet, we don't know building, the structure, the materials, we have to make certain assumptions. Let's say we don't have any, let's say we have no cooling, we have no heating or cooling in the building. The next best data we have is actually the outdoor temperature itself for the air temperature. Sounds a bit weird, but that's the only thing we have at the moment. But keep in mind that you could, if you think about it, if you research probably more and research on how the temperature changes from an outdoor temperature to indoor temperature through heat gain, solar radiation, the actual how the occupants change the temperature because people working in a space also change the temperature inside, then you can start to make adjustments. For now, just to show you the tool, I will use the same temperature as the outdoor temperature. It's as a starting point, I think it's reasonable. We can do that, but again, it's to use with caution, I would say. And then we have the temperature, air temperature for conditioned spaces. Well, the air temperature for conditioned spaces, we would need to assume that the air conditions the air to always like a specific temperature. It always tries to be in a range between, 19 and 23 degrees or something like that. So I would say we just have a slider here and we will provide the air temperature. We also need a run button, by the way. So we need to have a run button, Boolean toggle, copy. These are actually the two things we need to add. There's nothing more to add here. Now we already can check and see the comfort. Again, it's a bit tedious because we don't have an air temperature, but you can play with that. We don't have the air temperature. We could play with that. We could also research a bit how a building with certain insulation, shading, self-shading might influence the temperature and then influence our temperature, the outdoor temperature, so it fits an interior environment. So for example, now today, here it's pretty warm. I can imagine if I go outside, in the sunlight, it must be much hotter than here, and in the shade, it's probably cooler than here because I have wind breeze. Maybe temperature might be 3 degrees different. It's tricky because temperatures in winter might be warmer inside and so on. So it's a tricky approach. So that's why I will just stay with the outdoor temperature. I assume that people open their windows. It's always pretty much similar as outdoor, sorry. These are the items we need to provide in order to run it. We don't need anything else. However, you have optional inputs. So the mean radiation temperature, what is it? And I think we looked at this here before. Oh, we had the mat rate actually here. Okay, again, outdoor temperature, air temperature. Air temperature would represent the temperature inside. Because this is a building without cooling, heating, it's probably very similar than the outdoor temperature. But it's tricky to assume. But we don't have any other data at the moment. I can only use that. We have here an option which is called mean radiant temperature. And we will look at that in a second. We also have airspeed, and then there are some adaptive parameters, which we will look at everything. And then we look into the PMV comfort. Here's also a bit different. You also have the mean radiation temperature, relative humidity, airspeed, the mat rate. We talked about mat rate in the last video. Clothing, PMV parameters. So let's go through step by step. Here again, we don't need anything else to plot something out here. What could we look at? We look at if it's comfortable or not. We just grab another chart. We will use a point as a reference where in the plan it should be. You can use this one. And the data for it. And we need to run it first. Let's run it. Okay, true. That goes very quick. And we use the comfort here. Put this in here, data, and it gives us exactly when it's comfortable indoors and when it's not comfortable. Let's maybe look at this here. Interestingly, if I use the neutral temperature, it blocks out which months are comfortable and which daytime in these months. So it's just generalize it quite a lot. It's a bit too zoomed out to look at it. Let's see here. This could be more interesting. This is the temperatures. These are the difference. This is the difference to the required temperature. That means in order to make it comfortable, it would need to either be less or more. And that's why it says here minus 16. It seems it's too hot. It would need to cool down minus 16. And it would need to heat up. That's how I understand it. Anyway, let's go here. Comfort. So the red one shows now which area, which time of the day throughout the whole year is comfortable and which is not comfortable. So it doesn't really show us more. The mean radiation temperature. Okay, let's check that out. Can check it here. Ladybug, we go to Ladybug, analyze data, and mean radiant temperature. We need to use the Ladybug indoor solar mean radiant temperature. Okay, so this is what we use here. I think we did the same. Yes, we used the outdoor solar mean radiant temperature in the previous videos. So you probably already might know how it works. So we can put this here. We will need it for both. We need it for both tools. So let's put this here. Okay. This again needs the location. It needs a run button. Again, also the long wave mean radiant temperature. Again, it's super tricky. We don't know enough about what's going on. However, it's good to know the tool because we can gather information like this through Honeybee much later in the process. Anyway, let's continue. Long wave mean radiant temperature. A single number or an hourly data collection with the long wave mean radiant temperature around the person in degrees. This includes the temperature of the ground and any other surface between the person and their view to the sky. Typically, indoor temperature is used when such a surface temperature is unknown. So, okay, we don't have the indoor temperature, so let's just use the wrap-up temperature. Then it's asked for the direct normal radiation. Let's use the outdoor also here. The diffuse horizontal radiation. The fraction body exposure. A single number between 0 and 1 or a data collection for the fraction of the body exposed to direct sunlight. I assume, because we're indoor and we make it simple, we could use of course a model, but we don't have a model yet. So we will just assume we don't have any direct exposure to the sun. That's what I assume, okay? So direct sunlight. Comment then can be used. Estimate this input for a given set of context geometry and position of the human. Note that this parameter does not include the body's self-shading It only includes the shading from furniture and surrounding. Sky exposure, a single number between 0 and 1, or a data collection representing the fraction of the sky fault in the human suspect's view. The ladybug human to sky relationship component can be used to estimate its input for a given set of context. So again, we don't have a context. We could maybe just estimate how much percentage to see from a sky through your window, for example. Let's say I get, put this to 1, maybe 30%, 20%, maybe, and here's also, I need to go here onto 0.1, oh no, 1 as a maximum. So a single number between 0 and 1, so I just estimate. I just say, okay, we don't have direct sunlight, or maybe just in the morning, let's say a few hours. So I go for 0.2 maybe here. And then sky exposure, maybe 0.2 as well. So that's my sky exposure percentage, 20%, 20%. And of course you can play with it. That already gives you a way to play with thinking about your building, how big is the windows, and so on. Ground reference. Okay, let's check this. A single number between 0 and 1, or data collection that represents the reflectance of the floor. Default is 0.25, which is the characteristics for concrete. So let's use that. I could imagine that concrete is relevant here. Probably simple. Okay, we need more digits. 0.25. Okay, and we have window transmittance, sorry. A data collection or a number between 0 and 1 that represents the broadband solar transmittance of windows through which the sun is coming. Such values tend to be slightly less than the SHGC value, might be as low as 0.2 and could be high as 0.85 for a single pane of glass. Default is 0.4, assuming the double pane window with relatively mild low E coating. I don't know what they're using over there, but I assume the transmittance might be quite high. They won't probably use double glazing, so let's go with a high number for now. And we can research for your project what is the typical stuff people are using, and then you can see, if what happens if you change that, or it gives you an idea if you want to use double glazing, single glazing, and so on. The solar body parameters. So this is another tool we need to input, and you can find this here, I think, in Ladybug solar body parameters. Yeah, so we can put this in here. We actually moved quite away from this stuff, but we can already provide something. So if we now put this in here, let's see if this changes. Mean radiation temperature, that goes in here. Yeah. That changed a bit, so we now have a bit more time, which is comfortable, but it seems like it's not very comfortable in the night, probably too cold. And now we have other options here. We can change the posture. Standing, seated, supine. Let's say we are seated, panel, people sitting down. The next input here is about the angle of the sunlight. So if you're sitting in a way that the sun is shining into your face, that has an impact, of course. We just leave it as it is. The body AZ, a number between 0 and 360, representing the direction that the human is facing in degrees. It's interesting because these both deal with the sunlight, the solar horizontal angle relative to the front person. Yeah, we'll just leave that because we assume that you are that clever and you arrange your interiors. It's not constantly shining into your face, the sunlight. Absorptivity and emissivity. Absorptivity, a number between 0 and 1 representing the average shortwave absorption of the body, including clothing and skin color. Typically clothing was white, khaki, okay, maybe that also applies to skin colors. If it's brighter, it's 0.57, and then the darker the skin, the more absorption. Here we know, okay, we are in Kigali, in Africa, in Rwanda, Africa, and that means most of the people will have darker color or black color. So we go for maybe 75, even a bit higher, I think. Let's go with this. Doesn't change much. And then also the emissivity, how much the body... Oh, I put this in the wrong. I'm not sure if this actually changed anything because it doesn't really. Oh yeah, it actually changes a bit. And here says the emissivity is between, the default is 95, which is almost always the case, except in rare simulations of wearing metallic clothing. Okay, so that's emissivity. Pretty much provided input here everywhere. You could now, of course, play with this. What if I have more sun exposure? That changes things. Actually has a big impact. Sorry, my light is gone. Doesn't matter. The sky exposure has also quite an impact. Ground reference has, you can see there's quite a difference. And window transmittance. It's just better you have more transmittance to allow for more heat coming in. But let's look at the other components here. So we have airspeed. This is not the airspeed outside. This is the airspeed around the person. And the default is 0.1 meter per second. So I would say let's not change that. But of course you can always play with it and see what's changing. 0.1 meter per second is the airspeed. Just changes very slightly. Oh no, I took this thing away here. This was not a good idea. So now you're thinking, oh, why did it become more here? So if I have a ventilation or a fan, then actually I can improve, at least within this area, between 6 p.m. and 12 p.m. I can improve the temperature because it's about cooling it down. These gaps in between actually shows me that this blue area with between the red is uncomfortable because it's too warm. And whatever is outside is uncomfortable because it's too cold. And we could look at here you can see it's in the red areas, it's actually 6 degrees too hot to be comfortable. And then in the blue areas, it's let's say 16 degrees too cold. It's not minus 16 degrees, it's 16 degrees too cold to be comfortable. So, for example, here in August. So if we increase the airspeed, no, it's just minimal change really. You can't really see it on the chart. Hasn't really changed here because there's still areas with 6.7. But yeah, I hope you understand what I'm saying here. If I have a fan, maybe I can make this even higher. 5 meters per second. Let's go here again. Yeah, from a certain degrees it's not really changing that much anymore. I also add here this. In any case, that's how you could start playing with it. And there is another input here, it's called adaptive parameters. Let's check this out. Adaptive comfort parameters. I have this one. Let's move this a bit away here. What is this all about? Alright. I will not go super into detail because now it's getting to the finer grain, let's say. Here says the ASHRAE or EN15251. What is that? Okay, let's check what the tool does. Create a set of parameters that define the acceptable conditions of the adaptive thermal comfort model. These parameters can be plugged into any of the components that compute adaptive thermal comfort. And then here you can basically select between ASHRAE or the EN15251, which are both building standard models, which basically define some of these sets or the defaults for these sets below. The ASHRAE is American standard. The EN is a European standard. They both have their pros and cons. In that case, we could just select here true or false, just to test it out. I will not go into detail. You need to read about it yourself. I think it's something where when you have better clue about your building, if you're very clear about your building structure, materials and so on, then you might go into this a bit more and start reading about it. I would use just trying actually true and false. Just put here toggle actually. We can just put the toggle here. It's either true or false. For if we want to use the ASHRAE 55 neutral temperature function, that's true. And if we want to use the EN15251 function, then we use false. And by defining what we use, it also changes the defaults in here. So I will not go through that. You can read through it. it's always good to read. I did it myself, so I roughly understand what's going on. So for example, the first one, neutral offset. The number of degrees Celsius from the neutral temperature where the input operates between temperature where the input operative temperature is considered acceptable. The default is 2.5 degrees when the neutral temperature function is ASHRAE55 and 3 when the neutral temperature function is EN 15251. So you may want to use the set neutral offset from PPD or the set neutral offsets from the comfort class method on this object to set these values using PPD from the ASHRAE55 standards or comfort classes from the EN 15251 standard respectively. So again, if you go deeper and deeper into indoor, outdoor thermal comfort modeling, then you will learn more about this, and then you will also understand what's going on. Here you can also decide if it's conditioned or not conditioned again, how the outdoor prevailing wind might or temperature affects the indoors and so on. I will just keep it on false. I want to try to use the EN 15251 model, and I will just put this in here and see if there's any change. Yeah, changes a bit. It's very clear what it says. What it says to me is that the indoor is not comfortable during the night, and there might be some. So I can imagine that the right insulation might help to improve that without adding heating to the building. So it's actually more too cool than too hot. Interestingly. All right, guys. I can see we are already over the time. It's, as you see, it's not that easy. It's not that easy to really decide what's the right use, how we can measure it. I just want to test one more thing. So imagine I can get my indoor temperature right. What happens then? So if I, instead of like using the outdoor temperature here, let's disconnect. It doesn't work, of course. Now let's say we get through insulation, we get the temperature indoor right. It's always 21 degrees. What happens then? The air temperature. Interestingly, is not much different. So let's stay here, and we can revisit that if we want at some point and see when we know more about the building, then we can play with these values. Oh, okay, so this was the first part of indoor thermal comfort, and we will look at the PMV comfort in a bit. See you in the next video. I hope it's gonna be quicker. Ciao.